First of all, I'd like to thank the organizers, Professors Yeonjun Kim, In Kyung-an, Yuan-ro, and Shin-Chul-ae for giving me a chance to talk in such a nice conference. And this is the final day of the conference. Thanks to the kind hospitality of Professor Yeonjun Kim and In Kyung-an. This week is very valuable and comfortable for me, so I'd like to express my great gratitude. Okay, today I want to talk about kind of Lotka-Volterra competition models with diffusion and advection. This talk is based on recent joint work with Professor Toru Tsujikawa, University of Miyazaki in Japan. Okay, this is my contents of this talk. First, I want to introduce our PD model, the Lotka-Volterra competition model with diffusion and advection. This is our model. Here, omega is a bounding domain in n-dimensional Euclidean space with smooth boundary delta omega. And in this system P, unknown functions are U and V, which satisfies the homogeneous Neumann boundary condition on delta omega. This system arises in the ecological model, Lotka-Volterra competition model. So from such ecological model point of view, unknown function U and V represents the population density of two competing species respectively. At the position x moves in omega, and time t. Okay? So this is a couple of nonlinear parabolic equation. So left hand side denotes the time derivative for unknown function u and v, which consists of the combination of these two reaction terms. Reaction terms is a traditional Lotka-Volterra competition terms, and linear diffusion terms here, and the advection term in the second equation. Okay. Okay, let's see the reaction terms. Here, B1 and B2 are given positive constants, okay, which mean the birth rates of respective species, U and V. And these are also C1 and C2 are given positive constants, which means interaction due to the competition between different species. Okay? And in our model, intraspecific competition coefficients are normalized by 1, like this. Okay? This is Lotka-Volterra competition terms. And these are linear diffusion terms in which D1 and D2 are given positive constants, which mean the linear diffusion rates of U and V. So, which mean the linear diffusion of population density due to the Fick's law. Okay? And this alpha is a non-negative constant. This is a very important term, which means the advection. So this term describes ecological tendencies that the population density of the species V move from the high density area of U towards low density area of U. So these are natural setting because of the competition relationship. For the species V, the low density area of the competitor U is more favorable. So this is advection term. Our model contains the advection term in the second equation only. Okay? Okay, so our mathematical motivation or question is that what is a pattern driven by the combination of such reaction terms and linear diffusion terms, and moreover such advection terms. Today I want to talk about mainly the associated stationary problem. Okay? So this is a corresponding stationary problem, which is a Neumann problem for such a couple of nonlinear elliptic equations. Okay? Here I want to rearrange some coefficients in the diffusion and advection terms.
So this advection is very like the cross diffusion.
Yeah. Okay, here this D is equal to D1 for simplicity. Okay? And mu is here. So mu is equal to D2. But this is advection and diffusion. Here beta is here. The beta is equal to alpha over D2 in the linear system. Okay? This is our rearrangement for the explanation of our result. Okay? Okay, our interest is a positive solution of this problem SP. I will call this problem SP. Okay? Positive solution means the coexistence steady states of two competing species, okay? Whose both elements are positive in omega. Okay, this is our topics in this talk. First topic is the existence of non-constant positive solution. Among other things, non-constant positive solutions are important because such a solution may give a crucial clue for the stationary pattern. In this stage, I will give some sufficient condition for the existence of non-constant positive solution. And next, I want to a special case when this mu is very large. Mu is a diffusion and advection of the second species V. In such a case, I can derive detailed information of positive non-constant solution. Okay? Asymptotic behavior of positive solution as mu tends to infinity. More precisely, I want to derive a limiting system or shadow system as this mu tends to infinity. And moreover, in a special case, when omega is a unit interval, in a 1D case, in such a situation, you can find a global bifurcation structure of non-constant solution to limiting system. This is our program of this talk. Okay, before starting these topics, I should refer to a related famous problem. Okay, this is a very similar problem which consists of same Lotka-Volterra competition term and linear diffusion term, and moreover, this is slightly different. This is cross diffusion term. Laplacian you put here. Such a problem was first proposed by Professors Shigesada, Kousuke, and Tamoto in 1979 as a more general form. Okay? Since that time, many mathematicians in the field of reaction diffusion equation have discussed various viewpoints. Okay? As long as the stationary problem, I can refer to such a good result on the stationary SKT system. Okay? The group of Professor Masayasu Mimura began to study a stationary problem, and they constructed spiky solution, mainly by singular part advection techniques. And Professor Kang here gave you a stability criterion on such spiky solution and moreover bifurcation structures. And Professor Yuan Ro and Wei Min and Kim Liu and In Kyung An gave some result on the existence of non-constant solution, even including a full system. And moreover, Professor Ro and Ni drive a kind of limiting system as this cross diffusion beta tends to infinity. And they and Professor Yotsutani gave a detailed information on the 1D limiting system solution. And Professor Uyapi and Kolokonikov Bay recently gave a stability result on such a solution near a limiting system. And Professor Yoshio Yamada and myself have studied the limiting system as cross diffusion beta tends to infinity and the D-shape boundary condition case. Such as many results. compared with result on such SKT model. As far as I know, there are not so many works which specialize on the same competition model with advection terms. Okay? This is a reason why we began to study such a system. And to such a type of cross diffusion, as long as the stationary problem, I have an advantage. Okay? This system can be reduced to a semi-linear problem by employing a unknown function, this part, 1 plus beta u times point. So this problem can be reduced to a semi-linear problem as long as a stationary problem. Of course, in such a replacement, these two reaction terms become so complicated, so it will still be important to difficult problem. But for such a advection problem, couldn't reduce to a semi-linear problem without a first derivative function directly. So this is a technical reason why we began to study this problem. Okay. Anyway, let's study this problem. Let's begin with L infinity a priori estimate for every solution. Okay. Let UV be any non-negative solution of SP. So U element is always bounded to B1 here, B1 here. And V is bounded to B2 times such an exponential term. Okay? So here it is easy to check that this problem has a couple of semi-trivial solutions. Okay? Semi-trivial solution means a solution UV whose in which one of element vanishes. Okay? So SP has a two semi-trivial solution, U equals B1, V equals 0, and U equals 0, V equals B2. So I can say that this estimate for U is optimal because U equals B1, V equals 0 is a solution. But I think this estimate is far from optimal, so it should be improved. But here I want to say that these estimates up to now are independent of D and mu here, D and mu here. So this is a very important point. So such a L infinity estimate will play an important role in driving a limiting system as this mu tends to infinity. Okay? This is uniformly L infinity estimate with respect to D and mu. Okay, this is our first result on the sufficient condition for the non-existence of non-constant solution. Okay? Okay, let's regard this diffusion coefficient D as a positive parameter. Okay? And fix any other coefficient. So you can find a large number D bar such that SP has no non-constant solution if this D is larger than D bar. So this theorem 1 means large diffusion of the species U wipes any stationary non-constant solution out. Okay? So this theorem 1 can be proved by the standard energy method and the infinity a priori estimate, and moreover the Poincare built-in inequality. Okay? This is a standard approach. So I want to skip this proof. So here, against this theorem 1, we are faced with a natural question. This is the question. Does SP admit non-constant solution in a case when this D is small? This is a natural question. And this second question is also natural. Does SP admit non-constant solution even when this mu is large? Okay? If this advection vanishes, it is easy to know SP has no non-constant solution when this mu is large enough, because these two equations contain similar structures. Okay? But our problem contains such an advection term. So there is a possibility that the situation may change. Okay? Even when mu is very large, we can get a non-constant solution. This is natural question. Against these two natural questions, I will give positive answers and some assumptions. Okay? Before giving such answers, I should remark the positive constant solutions. Okay? All the possible constant solutions are easily obtained by solving these two algebraic equations. Okay? And SP has a positive constant solution if and only if the ratio B2 over B2 is between C1 and 1 over C2. The first case when C1 is less than 1 over C2 is called weak competition. Okay? This is UV plane, and these are corresponding nuclei in these parts. And in this case, such an intersection appears. This is a corresponding positive constant solution. On the other hand, the case C1 is larger than 1 over C2 is called strong competition. Okay? Also in such a case, such an intersection appears. Okay? This is a positive constant solution. Okay? Weak competition or strong competition. Okay, here let me show sufficient condition for the existence of non-constant positive solution. Okay? Okay, assume one of these two situations. Okay? The first situation, strong competition, and this beta is larger than 1 over C1 V star. Here, V star comes from V element of the positive constant solution. Or the weak competition, and this beta is larger than the same number, and moreover, this mu is large now. And one of these two assumptions, you can find the monotone decreasing sequence DJ. DJ approaches 0, the number J increases, such that diffusion D between DJ plus 1, DJ, and J is odd. Then SP has at least one non-constant positive solution. So this is a sufficient condition for the existence of non-constant solution. So roughly speaking, SP has a positive constant solution, and beta is larger than this number, especially in case when weak competition. Moreover, mu is large now. In such a situation, you can find infinitely many intervals of the diffusion D, such that SP has at least one non-constant solution. This theorem can be obtained by using the kind of degree theory. So this odd number condition comes from the index formula by Luray and Schauder. And this DJ depends on the J's eigenvalue of minus Laplacian with the homogeneous Neumann boundary condition. Okay? Okay. Here.
What if J is an even number? There is no.
No. Yeah. This is a sufficient condition. Sufficient condition. Yeah. Okay. Okay. Here, let me show such a situation in a special case when omega is an interval. In such a simple case, this theorem can be interpreted by using the bifurcation term. Okay. Okay. This is a one-dimensional version of SP. Okay. Omega is an interval. And this is a very rough sketch of a bifurcation diagram. Here, this is D-axis. This is UV axis, okay, which is in suitable balance space. But okay, today, let's regard this axis in L infinity space. Okay, L infinity space. This is for explanation. Okay, rigorous theorem. Can be described in the more regular space, for example, W2P space. But for explanation, regard this axis in N infinity space. Okay, and in the case strong competition case, beta is larger than this number. Such a situation, J mode solution bifurcate from the positive constant solution U sub with the up to D equals to DJ. So in 1D case, DJ is a bifurcation point from the positive constant solution. Okay, positive constant. This line denotes the positive constant solution, which independent of D. So this is a line. So this is the first bifurcation point, D1 here. From here, monotone solution bifurcate from the, this is the profile of U and V. Monotone solution bifurcate from the positive constant solution like this. And the second bifurcation point, two-mode solution bifurcate from the positive constant solution like this. This is a strong competition case. And weak competition case, for example, a stability structure wholly changes, but if beta is larger than this number, mu is large enough. In such a situation, we can draw a similar bifurcation diagram. Okay? Okay, so here recalls our first L infinity a priori estimate. So any solution is bounded by, uniformly bounded by some positive number. So we can say that any solution, any extension of this local curve of local bifurcation curve cannot beyond this bounded line. And recall the first theorem. If D is large enough, there is no non-constant solution. Okay? So together with the global bifurcation theory, we can say that any extension of local bifurcation curve as a set of non-constant solutions cannot go out of such a cage. Okay? And we can say that this extension satisfies the following, one of the following two situations. One possibility is approaches another bifurcation point, another bifurcation. The second situation approaches singular limit. Okay? But generally speaking, to conclude which of these occurs is very difficult in the field of reaction diffusion system. So in order to give an answer against such a crucial question, what shape is the bifurcation branch of non-constant solutions, I want to study a special case when this mu is very large. Our aim is now to derive a global information of this curve in a special case when this mu is very large. So let's move on the second topic. Okay, symptomatic behavior of positive solution as mu tends to infinity. Okay, so ecological viewpoint. This mu, this is a rough observation. Mu means the activity, a kind of activity of the species V, because V is diffusion and advection. Okay. First, I want to drive a limiting system as mu tends to infinity. Okay, shadow system. Let's begin with a formal derivation of such a limiting system. Okay. Okay, this is our original problem, SP. Driving limiting system holds for general domain case. Okay. And let's see this second equation, and divide this second equation by mu, and letting mu tends to infinity. So this reaction term vanishes like this. Okay. And next, integrate this second equation over omega. So thanks to the Neumann boundary condition and the divergence theorem, vanishes this part for each mu. So for each mu, integration of this second reaction term is always equal to 0. So the limiting case, such equation preserved. Okay? So formal derivation. So our limiting system consists of the Neumann problem for such a couple of elliptic equations and such an integral equation. Okay? And this couple of elliptic equation can be reduced to a single elliptic equation. Okay? Okay, let's see this second equation. And employing new function w as v times exponential beta u. So it is easy to check that this second equation is equivalent to this equation for w and u. And taking the Earth's inner product, this equation with w implies this integration is always equal to 0. Okay? Here, this exponential term is positive. So we can say that w must be a constant. Okay? So set this constant lambda tilde. So v equals lambda tilde exponential minus beta. So by substituting this relationship into here, and here, so you can get such a limiting system which consists of the Neumann problem of such a single semilinear elliptic equation with the exponential term and such an integral equation. Okay? In this problem, unknown function u only. But the important point, new parameter appear, lambda tilde, here and here. Roughly speaking, another unknown function v is replaced by new parameter lambda tilde by limiting procedure. Okay? Okay. Anyway, this is our limiting system. But this is a formal derivation. Formal derivation can be justified under the assumption the ratio B2 over B1 is not equal to C1 and moreover is not equal to 1 over C2. Under this assumption, let UN Vn be any sequence of positive solution of SP with mu n tends to infinity. So you can find a limit positive function u and positive parameter lambda tilde, such that UN approaches u, Vn approaches this function, and this limit function satisfies this Neumann problem and this integral equation. Okay? In the sense of this theorem, this system N and I is a shadow system or a limiting system of original system as SP mu tends to infinity. Without this assumption, convergence is whole, but this limit function may be a semi-trivial solution. So in order to remove such a situation, we impose such assumption. Okay? Okay. Anyway, this is our limiting system, N and I. But C1 and lambda tilde are both constant, so we had better reform some coefficients. So, for example, this part is replaced by new parameter lambda. So this lambda tilde is replaced by lambda over C1, such a way we rearrange of coefficients of this N and I. Okay, this is our limiting system, rearranged limiting system. Here, this A is equal to B1 in the original system, and this B is equal to B2 C1 in the original system, and this C is equal to C1 C2. Okay. Okay. Hereafter, I want to solve this limiting system in the special case when this omega is an interval. Okay? In a simplified one-dimensional case, this Neumann problem is a two-point boundary value problem for such nonlinear ordinary differential equations. Okay? And I is integral constraint, non-local constraint over the unity interval Z1. Okay? This is our strategy analysis of N and I. First, forget such integral constraint. Concentrate on the Neumann problem, N. Okay? And collect all solutions of N. Next, check the integral condition, this I, for each solution of N. By such a way, let's construct the global bifurcation curve of solution N and I. Okay? Okay, let's start with the first stage. Forget the integral constraint and focus on this Neumann problem. Okay? This nonlinear ODE contains 4 parameters: D, A, lambda, and minus beta. Okay, this is nonlinear term. Okay? Nonlinear term contains 3 parameters: A, lambda, beta. Okay. First, fixed A positive arbitrarily, and regard lambda and beta as positive parameters. Okay. This is lambda beta plane. First, let's think about constant solution. This is a Neumann boundary condition. Okay. This is a very basically but very important point. It is easy to check that straightforward calculation implies as N has a couple of positive constant solutions if and only if lambda and beta belongs to this purple region sigma. Okay? This sigma consists of beta, this is beta axis. Beta is larger than 1 over A, and lambda is larger than A, and less than exponential A beta minus 1 over beta. Okay? This curve. Okay, these profiles are corresponding to profile of nonlinear term F. This is U axis, this is F axis. Okay? So you can see that only in this purple region, this F possesses a couple of zeros, positive zeros. Okay? Like this, 2 zeros. Outside of purple, the number of positive zeros, at most one. Okay? This is a very important point. And moreover, it is easy to check that such a situation, this problem N has a non-constant solution for some D if and only if lambda beta belongs to this purple region. So hereafter, we have only to discuss the case when lambda beta belongs to this purple. Because what I seek is non-constant solution. Okay? Okay. So fixed here, beta fixed being larger than 1 over arbitrarily, and let regard this lambda as a parameter move from A to exponential A beta minus 1 over beta. Okay. In such a situation, N has 3 non-negative constant solutions. U equals 0 and 2 positive constant solutions, M lambda and L lambda. This is a middle constant solution. This is a large constant solution, which depend on parameter lambda. M lambda is monotone increasing with respect to lambda. L lambda is monotone decreasing with respect to lambda. Okay? These are profile of nonlinear term for each lambda. And this integration is very important. This is nonlinear term over 0 L. L is a large constant solution. Okay? And it is easy to check that this value is monotone decreasing with respect to lambda from positive to negative. So you can find a unique number lambda star such that this integration is equal to 0. This is a very important number. I will call this number lambda star balanced number. Okay? Balanced number. So if lambda is less than the balanced number lambda star, this integration is positive. Lambda is larger than lambda star, this integration is negative. Only in the lambda is equal to the balanced number, this integration is equal to 0. Okay? As some talks in the conference, PDE with such type nonlinearity is called a bistable equation. So in such a situation, small constant solution and large constant solution are stable in some sense, and middle constant solution is unstable in some sense. This is a very well known property for such a bistable equation. Okay? And moreover, it is well known that profile of solution U with small diffusion D drastically changes when this lambda passes balanced number lambda star. This is a universal property for the bistable equation. Okay? If lambda is less than lambda star, okay, let me show a rough sketch of the corresponding phase frame. This is orbits of corresponding solution to initial value problem of this OD. Okay? If lambda is less than the balanced number lambda, so you can find the homoclinic orbit from origin to origin here. And lambda is larger than this balanced number, there is a homoclinic orbit L from L to L here. But in the special case when lambda is equal to the balanced number lambda star, there is a heteroclinic orbit from origin to L. And this is a well-known property. If diffusion D is very small, by kind of rescaling, the profile of a solution U, monotone solution U, is near such a homo or heteroclinic orbit. So this is a very rough reason why the shape of a solution U drastically changes when lambda passes lambda star. So structure changes. Okay. Okay. Anyway, we can get a region for the existence of non-constant solution of n only on lambda D plane. Okay. Here fixed beta orbital which being larger than 1 pi. Okay. Okay, this is lambda axis. Lambda moves from A to this number, and this lambda star is a balanced number. Okay. Okay. Lambda fixed here, which is less than lambda star, fixed here, and make diffusion D decreasing on this line. So hit the green curve. This green curve plots the bifurcation point from the middle constant solution M lambda. So from this point, monotone increasing solution bifurcate from middle constant solution. This is the profile of solution. Middle constant solution M lambda, and approaches 0 in LP sense as D tends to 0. But the important point, the right-hand value remains positive. So if D is very small, you can find such a boundary layer solution. Boundary layer appears near the right wing. And lambda fixed here. and make D monotone decreasing. So hit this green curve. This is the bifurcation point. Okay? From this point, monotone increasing bifurcate from the middle constant solution M lambda and approaches L. L is a large solution in LP center. But the left end value is strictly less than L. Even the limit case D equals 0. Okay? So you can find such a boundary layer solution if D is very small. In a special case, when lambda equals lambda star, monotone increasing solution bifurcates from the middle constant, so M lambda star, and approaches a step function as D tends to 0. But the location of the step is the exact center of 0, 1. So x equals 1/2. 1/2. Okay? Okay, hereafter, I want to discuss monotone increasing solution only, because any other solution, oscillating solution, can be constructed by kind of rescaling and connecting such monotone pieces, okay? For such a one-dimensional autonomous problem, okay? Okay, we can such a region by using so-called time mapping method, traditional time mapping method, developed by, for example, Smoller, Wasserman, or Sha. Okay, we are now ready for check the integral equation. Okay, this is our crucial stage. Okay, for each solution. In other words, each point of this curved region. Okay. Okay. Today, I want to introduce such a global bifurcation result by using lambda D plane again. Okay. So formal description is slightly wrong, so it is hard to understand. So I want to use this plane for explanation. Okay. Okay. This theorem states the case global bifurcation structure of N and I in the case when C is less than 1. C is less than 1. Okay? And global bifurcation structure can be classified into 4 kinds, depending on B. B is here. B is in the integral constraint. Okay? This is B axis. This is a meta of B. Okay? Okay. B is between these two numbers. This is a corresponding bifurcation curve, okay? Which comes from this figure. Okay? So this red curve means a subset of monotone increasing solution of N and I. And first let me see, this curve is apart from this dot green curve. Okay, this dot green curve is not contained. Is not contained the set of solutions. This is for only for the explanation. This fact means every solution on this red curve is apart from the constant solution. So this is a saddle node type bifurcation curve. Okay, and this curve connects these two different singular limit D equals 0. D equals 0. And this left 2 is corresponding to the internal layered solution because lambda equals the balanced number lambda star. Okay? Okay? Near this point, any solution U possesses an internal layer. But here, what I want to say that the location of the internal layer is not always equal to 1/2. 1/2. This location depends on B. Okay, move depending on B. Okay? And this right 2 is corresponding boundary layer solution. Okay? This is the profile. Solution U almost equals to L. L is a large constant solution because lambda is larger than lambda star. Okay? And as B increases, B crosses this number. This left 2 does not move, but this right 2 move. and remove from this singular limit touch the green curve. In this situation, monotone increasing solution bifurcate from the constant solution here and approaches internal layered state as D approaches there. And as B increases, this curve turn anticlockwise and B beyond A. This point come back to the singular limit like this. In this curve, this is a corresponding boundary layered state. U almost vanishes, but near right end, U is drastically increases. Okay, and this is a location of the singular limit. This point. Okay, this is the location of internal layer. So this expression depends on B. Okay, here I want to explain this theorem by using a very rough cartoon. Okay, this is a somewhat feeling. Okay, this is B meta. This is a B axis. This is B axis. This is a corresponding bifurcation diagram. This is very rough sketch. And this profile is corresponding to the singular limit. This point, D equals the lambda equals lambda star. Okay, okay. Let's B increases. So B increases in this range. So this arch becomes large, and this internal layer moves from left to right, and B crosses this number, this right to touch the green curve, and B increases this curve turns anticlockwise, and moreover this internal layer moves from left to right, and B beyond this number come back to the singular limit, and as B is crosses dim lambda star, this curve becomes small, and finally B attains this lambda star. This bifurcation branch disappears. Point this D equals 0, lambda equals lambda star. At the same time, this internal layer attains the right end. Okay, this is a very rough story of this global bifurcation structure. Okay, like this, as being. Okay. This is a result in the case when C is less than 1. Okay, C is equal to C1 times C2 multiplied of competition coefficient. Okay, so this situation contains a weak competition case. Okay, and moreover, I should say that this bifurcation curve can be obtained, can be proved by almost all value B. Not all. Our rigorous proof cannot help relying on the kind of third theorem. So up to now, this result obtained for almost all value B. Okay, and moreover, the detailed information, for example, the exact number of this turning point cannot be proven. Okay, up to now, this is our near future crucial problem. Okay, okay. So sorry, skip the proof. And another case when C is larger than 1, the global structure of N and I drastically changes like this. But in this case, we can obtain such 4 kinds of bifurcation curves. Okay, this is B axis. Okay. Okay. Let me go back. Original system. Okay. This is our conjecture. If I can construct the bifurcation curve near the limiting solution curve by the perturbation, I can send that such a situation to the 1D original case. If mu is very large, for example, such a situation occur. Monotone solution bifurcate from the first bifurcation point and approaches such a internal layered solution. Internal layer solution is corresponding to segregation. Okay, because, for example, this figure. Sorry. Go back to the. For example, such a case. This is a constant solution. Approach is a singular. So, for such a curve can be constructed. But another situation. So, we may get such a curve which connects these two different singular limits. One is a boundary layered state, one is internal layered state. Okay. This is our near future problem. Okay, I should stop here. Thank you for your kind attention.
So, are there any questions?